Hello and welcome back. We continue with year 13 trigonometry, proving trigonometric identities. I think the last time we reached up to question 12. We're going to continue now from question 13. Try to do as many as we can, probably in about half an hour. Just try to show you different techniques of how to do things now with this one. Okay, question number 13. We're trying to prove that the cos of sorry, it's not a cos, it is a cot of 2x. I beg your pardon. Let me just I'll cover the question and then I'll move out of the way in a second, guys. Cot of 2x plus the cosec of 2x. We want to prove that is identical to the cot of x. So this is question number 13. Okay, left hand side or right hand side? Well, quite clearly it's a left hand side job, so we're going to start with the left. And what can we do in there? So we just we got obviously to break the double arguments. Because we have the cosec, it's probably better to go in sines and cosines. So we're going to write it as a cos of 2x, that's my cot, over the sine of 2x. Cot is cosine over sine, plus 1 over the sine of 2x, and that's very pleasant because of course we've got same denominator, and this is the cos of 2x plus 1 over the sine of 2x. And now what do we do? Well, we need to clearly go into single arguments, the single x. So for the sine of 2x, there's only one choice there, is the identity 2 sine x cos x. That's the sine of 2x. What do I use now on the top? The cos of 2x has 3 versions, and the version that I need there, I did mention it. I'm not really looking, do I need causes or sines? Nothing of the sort. I need the identity that gets rid of this one, and the required identity, I'm going to write it in red in there, is the one that says that the cos of 2x is 2 cos squared x minus 1. The reason for that, we got a minus 1 plus 1, and this will now cancel. And after that, hopefully, we're going to get our required answer. The ones now cancel, so I'm going to get a 2 cos squared x over 2 sine x cos x. The 2's cancel. I can get rid of one of the causes. I'm going to get cos x over sine x, which of course is the cot of x, which is RHS, and the question is done. Okay, so that was question 13. And we're going to go to question 14. And let's see what it says. It says the sine of 2x is equal to 2 tan x over 1 plus the tan squared of x. Okay, this particular one, those who are doing further maths, you should really recognize this. It's one of your little t identities. She's the one that says basically the sine of x is 2t over 1 plus t squared when you're using, I think it's on currently the FP3. I don't know, I've lost the track of things now with the exams. Okay, for us here now, where do we start with this? I don't want to start from the left because of course I start from the left. What do I do after the sine of 2x? Quite clearly, left hand side, sine 2x, 2 sine x cos x, and now brick wall. So we're going to start for this one on the right hand side, RHS, and we're going to say, okay, what choices do I have? Is this an identity? It is an identity. 1 plus tan squared is very special. So the first thing I'm going to do is I'm going to write it as sec squared of x. It's a standard result. Please make sure when you're doing this kind of work, you have a reference sheet with all your identities, and you refer to it until you learn them. Not only you need to learn them, but you need to actually be able to see things in the algebra. So from there, how I'm going to simplify that, I'm going to write the sec squared of x. Oops, there's no square there. On the top, if I move it to the top, it becomes now a cos squared of x. I'm going to switch into sines and cosines. So the tan, of course, will become sine x over the cos of x. So that's my tan. times the cos squared of x, and everything just flows. Cos squared will be cancelled with the cos at the denominator there, so I'm going to get 2 sine x cos of x, which of course is an identity. That's the sine of 2x, which of course is now the left hand side. By the way, if you didn't spot this identity, it will still work if let me just show you. I'm going to try to squeeze it in there. I don't know if it's going to be visible if I write smaller. I can switch this into sines and cosines as it is. So this will become 1 plus, actually what I will probably do there, it might be a good idea to perhaps rub the line above. I'm going to have to rub it off anyway to make some space so you can see it better. So that's gone. That was question 13. And let me just take off that as well at the bottom. So if you look at this, you could have actually written it as sine squared x over cos squared x, and then write your tan as sine of x over cos of x. Now if you multiply top and bottom of this fraction, which consists of 3 terms, 1, 2, 3, by the cos squared of x, okay, so can you picture it? Cos squared x. I'm writing the workings for the benefit of people that are not quite sure what I'm doing in there. Okay, so imagine all of this have been multiplied by cos squared. What will happen in there? First of all, this will cancel, gone. On the denominator, which is easier to see, I'm going to get a cos squared x on the left. That's 1 times cos squared, plus this is gone, sine squared. Beautiful. On the bottom, of course, this will be 1. And if you look what happens on the top, I can cancel that with the squared. So I'm going to get a 2 sine x cos x, which of course is going to be denominator 1, identity on the top, which of course will take me back to the same expression I started with. So that also works very, 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 very well. Okay, so even if you don't spot the Pythagorean identity, it does not really go to complicated workings. Okay, let's go now to question 15. Question 15 says sec squared of theta over 1 minus the tan squared of theta is identically equal to the sec of 2 theta. All right, clearly start with the left hand side for this particular one. What can I do? The question is, of course, I need to go from single to double. And when will I know that I'm done? I will know what I'm done. So I'm just doing a little bit of forward thinking when I get 1 over cos 2 theta. And when will that be the case? Working backwards, what must it look like on the denominator? It will either look as cos squared theta minus sine squared theta, or 2 cos squared theta minus 1, or 1 minus 2 sine squared theta. So essentially my target for this particular question is to start from the left and somehow end up with one of these 3, because this is in fact the cos of 2 theta, and if I have 1 over the cos of 2 theta, then is my answer. So what do I do for this particular one? Well, quite clearly, probably the best thing to do there is to switch into sines and cosines, like I just done on the second version of question 14. So this is going to be 1 minus sine squared over cos squared. That's, of course, is my tan squared. And my sec squared on the top is 1 over cos squared of theta. What happens next? Well, quite clearly, the technique that I've just used many times before in the first lecture, as well as this one. So I'm going to multiply top and bottom of this fraction by the cos squared of theta. See if you can follow it. I'm not going to write it this time. Times it by cos squared, it leaves me 1. Times by cos squared, it leaves me cos squared. Times by cos squared here, it will cancel the denominator of this particular fraction. So it will leave me minus sine squared theta. And of course, after that is really this line here. That will be 1 over the cos of 2 theta, standard identity. into a definition, into equal R8 says. Question 15 is done. Okay, so this was question 15. They become repetitive after a little while. Trigonometry does cause problems, but it is problematic if you don't put the work in. If you put the work in, then eventually it's not as bad as you first thought. Number 16 looks a little bit unusual. The tan of 2 theta minus the sine of 2 theta over the tan of 2 theta is the same as, is it 2 sine squared theta? 2 sine squared theta. So this is the identity we're trying to prove. Quite clearly, we're going to start from the left. A lot of stuff there. We also need to break the 2 thetas everywhere because the other side has sine theta. What choices do I have there? Well, if I start from the left, there's 2 things that come to my mind, and I think both of them they will be okay. They will just simplify nicely. One is to split the fraction. Okay, so I'm gonna have tan 2 theta over tan 2 theta minus sine 2 theta over tan 2 theta, and then I'll probably switch into sines and cosines. And the other one is to switch into sines and cosines straight away as it is in there. Because I'm trying to make the video a little bit shorter, I'm not going to be showing 2 versions for this one. I'm going to do the split the fraction version for this particular one, but you can try to switch into sines and cosines and use techniques like I used on the previous couple of questions. So if we split the fraction, tan of 2 theta divided by the tan of 2 theta is 1. Then I got a minus sine of 2 theta over the tan of 2 theta. Okay, most people now would have probably put a double fraction for something like this. I do sometimes, and it's very difficult to explain when do you switch into a double fraction, like I've done a couple of examples ago, and sometimes I say, oh, I'm going to move that to the top next to it, but call it something else. For this particular one, because it is so simple, I'm going to leave the sine of 2 theta where it is, and if I move the tan next to the sine of 2 theta, tan changes name to its reciprocal, which is of course the cot of 2 theta. That's much easier to actually handle. What will happen in there? Well, one, I'm not breaking the double angles yet. I'm going to switch that into sines and cosines first. Sine of 2 theta, and the cot is of course the cos of 2 theta over the sine of 2 theta. Lots of beautiful things happening. So I can cancel the sine of 2 theta. So now I have 1 minus the cos of 2 theta. And this is my target. How do I get to my target? Very, very easily. I just rubbed off the identity I had up there for the cos of 2 theta. This is an identity which you need to know by heart. The cos of 2 theta has 3 versions, and I'm going to use the sine only version, which says 1 minus 2 sine squared theta. And what will happen in there? The 1 minus 1 cancel. Minus times a minus is a plus. 2 sine squared theta, which of course is my target, my right hand side. And that is question number 16. Question 17 coming up next. I think this particular question came up in an exam. So quite a while back. A lot of people, it was part of an equation actually. The identity, it was hidden within an equation question, and it caused a lot of problems. So let me just write it and let's see what this says. Number 17, sine of theta over 1 plus the cos of theta plus 1 plus the cos of theta over the sine of theta. So the same thing but upside down, okay, is equal to, identically equal to 2 cosec of theta. What shall we do for something like that? Well, clearly left hand side. Decision number 1 sorted. Decision number 2, what do I do with these things? I don't think we have much choice there but to add the fraction. I cannot see anything else sensible but to put the two fractions together. So algebraic fractions, adding fractions in general is actually very important now for this particular one, and also not to panic because we got trig quantities. So the lowest common multiple is that times that, 1 plus cos theta multiplying the sine of theta. Now, you know that some people kind of see that as multiply the sine across and the 1 plus cos across. That's fine, it's the same thing. You can think of it also as multiply top and bottom of this fraction by sine theta, and top and bottom of this fraction by the bracket 1 plus cos theta. Both of them are equivalent. So whichever way you do it, I'm not going to be teaching you here how to add algebraic fractions. We're going to get this as our first line. And after that, quite clearly, let me move this cable out of the way because I might trip, is to tidy up a little bit. Now, sine squared of theta, I'm thinking a little bit ahead. I'm going to get another cos squared from in there, so that'll be a 1 somehow to be created. So let's keep track of things. So it's going to be 1 squaring that, multiply together and double 2 lots of the cos of theta plus cos squared theta. And shall I multiply that? The answer is no. That's what is the key thing about this particular question. I'll tell you why. It's because you need to think a little bit ahead. And if you multiply, you need to remember when it happens to actually take it back if there need be. The answer that you should get, so you're proven basically, is 2 over the sine of theta. When you get that, you can say, okay, 2 over sine theta is 2 cosec theta, done. Look at the sine theta in there. That is there. So I don't want to multiply it out and lose it. What it's actually telling me is this bracket here somehow, once I tidy up my top, they'll be cancelling somehow to leave me hopefully a 2 on the top over sine theta so I can finish it. So I'm going to leave this for the time being as it is. 1 plus cos theta over sine theta. This now identities are getting a little bit harder, obviously. So sine squared of theta plus cos squared of theta is 1, plus the 1 there, altogether 2, with this 1 there, plus 2 lots of the cos of theta. And I hope you can follow now better what I was referring to a minute ago or so, because now if you look at the numerator, I can factorize the 2 and this bracket, and that's why I didn't want to multiply it, will appear also on the numerator. So now the question is well and truly over. Game is up. So it's 2 over sine theta, which of course is going to be 2 cosec, which is equal to RHS. So question finished. That's a little bit more involved, and I did explain this question when it came up. It did cause problems. A lot of people multiplied too many things and they couldn't quite see, amongst other mistakes of course, it wasn't the only problem, how to get to the final answer for this particular question. It's not as bad once you've seen a couple of items in there. So that's question 17. Question 18. The cos of, this is 18. The cos of 2 theta is equal to 1 minus the tan squared of theta over 1 plus the tan squared of theta. This is another one for the further mathematicians that might be looking at this. It's another one of the little t identities. The cos of theta is 1 minus t squared over 1 plus t squared. If you recognize, if not, do not worry too much about it. Okay, where do we start with this? Definitely right hand side, and probably the plan for something like that is this is an identity. I know, for example, this bit here is a sec squared theta, which then I can move to the top as a cos squared, but I'll still have the 1 minus tan squared. So for this particular one, this is the kind of thing which is very difficult sometimes to explain why on this one I'm doing this approach and on another I'm doing something completely different. Mathematical gut feeling is not something that can be taught. You need to have a lot of practice, and then you develop your own style and your own feel for things. For this particular one, my style is to switch into sines and cosines without a shadow of a doubt. I think that's actually longer to switch into sec squared and then move the sec squared to the top. So I'm gonna take that off. I saw it, but I chose not to approach it this way. So sine squared theta over the cos squared of theta, and similarly 1 plus sine squared theta over cos squared theta. And now I will kill that very, very quickly. Guess what I'm gonna do? I'm going to multiply top and bottom of this fraction by cos squared theta. 1, 2, 3, 4 lumps, all multiplied by cos squared theta. 1 times cos squared theta, cos squared theta. Stick a cos squared theta here, it will cancel me there, minus sine squared theta. On the denominator, cos squared theta, on the bottom left, and then when I times by cos squared theta here, plus sine squared theta. And this is over, well and truly over. This is one identity, and this is also an identity, which of course is the cos of 2 theta. Nothing else to say, it's equal to RHS. Okay, it looks very scary when you first look at this, but is how many lines is that? 2 or 3 lines. It's all done. Okay, so question 18 finished. How many marks questions like this will be worth in an exam? Probably about 3 marks, something like this. Sometimes you might get generous for occasionally. And normally it'll be a show, obviously, some trigger identity, and there'll be sometimes a follow-up, some equation perhaps to be used in the latter part of the question, or some kind of manipulation and so forth. So this now is very unusual. We don't often get square roots in identities. I mean, how am I going to simplify that? Sorry, I didn't put the right hand side. That's even funnier. Okay, what's that equal to? It's equal to, I wish I could see it, 2 cos theta. Identically equal to. Okay. What do I do with this? A little bit of thinking. Definitely left hand side. At least I took care of one of my decisions. Because I got a square root, it should be obvious, and on the other side quite clear I haven't got one. I must have somehow created a squared expression inside the square root. Okay, so I'm trying to think, what could I possibly do? There's another thing obvious, which is 2 theta here but theta here. So that is telling me I need to somehow break my cos of 2 theta. 2 plus 2 bracket blank close square root is equal to. I have now 3 choices for the cos of 2 theta. Cos squared theta minus sine squared theta. I don't fancy that. I have, of course, the 1 minus 2 sine squared theta. Let's put it in there just to see what happens. 2 plus 2 is 4. So I'm going to end up with 4 minus 4 sine squared theta. Will it work? Yes, it will work, but I'll do another unnecessary another necessary step after that, and it will work. It's probably better to go for the one I left last, which is 2 cos squared theta minus 1. Why is that the one that I'm after? You might say it's because I got cos in there. It's actually more than that. It's because this particular one we will end up cancelling that 2 at the front. So let me just write it in so you can actually see it. 2 cos squared theta minus 1. This is what will happen. 2. I need somehow to lose this 2. Plus 4 cos squared of theta minus 2. And that is equal to this quantity here. Now, I don't want to open a can of worms and start talking about moduli and things like that. This is from a standard A level. This is what the question that was given to you says. Please do not question things further. The answer, if you square root that, is of course 2 cos theta. And if you didn't even notice what was the problem there, it's even better. You can put RHS and move to the next question. Those who are screaming behind me now say, oh, what about modulus or whatever? It's an A-level question. It would have been written like this. Yes, you can, strictly speaking, you need some conditions in order for that to be true, but we just ignore them for the time being and just treat this in a very simplistic way. Okay, question 20 next. This is not very interesting. This one's from EdExcel from a while back. It's early 2000s, quite boring. Total lack of inspiration really on this question, but let's write it. We have to prove that the 3 sine theta plus 5 times the cos of theta all squared is identically equal to 17 plus 8 lots of cos of 2 theta plus 15 lots of sine of 2 theta. Okay, we have a little bit of contradiction here with this particular question when we try to start it. The first one, is it left to start with or right? Common sense says go left, because I got the square bracket, okay, so it's probably easier to square it. But then on the right hand side that I'm trying to get to, I've got the 2 thetas, and I know identities that convert me from cos of 2 theta to theta. So the question is, what do I do? And also they look pretty ugly on both sides, so I could have easily started from either side. The fact of the matter is, somebody who's able and good and exam standard, you can do it either way without any problems. It's actually just as good, but we're going to start from the left ourselves, because that actually, for somebody who is learning, is probably more natural. So we're going to square this bracket. Square the first thing, 9 sine squared of theta plus, multiply together and double, 15 30 lots of sine theta cos theta. I like this term. Sine theta cos theta with a 2 at the front is the sine of 2 theta, and 15 and 30, I don't know, something's going on in there. Plus, square this second bit, which is of course a 25 cos squared of theta. Okay, now I need to put my thinking cap on. This bit, let me just say, okay, that's definitely 15 lots of 2 sine theta cos theta. That's another way of writing this, which of course is simply 15. That's an identity. The sine of 2 theta is of course that, and therefore I have part of my answer. At least I have got a bit of my answer. What do I do next? What's the best way to proceed from there? There's several variants, but my favorite for something like that, if I was doing that for myself, is to actually waste a line and rewrite this as 9 sine squared theta together with this. Since I have to use the 2 lines for that anyway, so I'm quite happy to waste a line there to do other things. And this 25 lots of cos squared theta, to write it as 9 lots of cos squared theta. So I got 9 sine squared theta plus 9 cos squared theta, and I've got, how much I got left in there? I've got there 16 lots of cos squared theta, so I can balance it. Okay, equal and equal. Just so we can all see and you're happy what I'm doing, this is going to be my leading term now. That's this term here. I'm going to put plus 9 lots, bracket, sine squared theta plus cos squared theta. I'll just put those 2 terms together and factorized. I could have done it in one. Of course, most people can see that this is 9, but I'm just doing it in steps because I want thinking time to decide what I'm going to do with this. Plus, of course, my 16 cos squared theta. Let's waste another line and just do a bit of a tidy and just see what happens. Of course, this is 1. So far I've got 9 from this term here. plus 15 sine 2 theta plus 16 cos squared theta. Those who have followed my integration lectures, which come obviously after you normally do trig, you would know, of course, and you can use it here, that, you know, when we're integrating sine squared and cos squared, there's some special identities which I use, which are basically rearrangements of the cos of 2 theta. And I say, look, the cos squared of theta and the sine squared of theta, the same as a half plus a half cos 2 theta, and the sign is exactly the same, but with a minus. So I could have actually finished the question off by putting 16 times that. But some people might not have seen these identities before, they don't use them, and they prefer to go through the double angle every time. So I'm going to put the alternative. So first of all, choice number 1, take this identity, plug it on the cos squared theta, simplify, you get your answer. The alternative is to start with your cos of 2 theta, which is the missing term really. This is the term that we haven't got into. So we need something that has cos 2 theta. And write it as 2 cos squared theta minus 1. And then rearrange your identity as 1 plus cos of 2 theta is 2 cos squared theta. And then probably, since I want 16 of them, multiply the whole thing by 8. So it's going to give us 8 plus 8 lots of cos of 2 theta is equal to 16 lots of cos squared theta. So if we look at this line now, and we look at what we got, I managed to create now here plus 8 cos of 2 theta. So my answer now altogether, 9 plus 8 will be 17, plus 15 sine of 2 theta, plus 8 lots of cos 2 theta, which I believe was RHS. Okay, quite an involved question. It's not actually a beautiful or an elegant identity. The reason this question, as I said, comes from Excel from the early to mid 2000s, can't quite remember the year, is purely because what was following in the question, there was I think that was part A possibly, there was a part B and probably a part C, and you had to do other manipulations, and you needed this answer to do the next part, and that was what this question was all about. Okay, I'm going to finish off with question 21. That's going to be our last question for today. So I had no idea how far I will go. I think that's probably enough. It will be a good place to stop. So we go to question 21, and that will be the end for today. Let me write the identity. 1 plus sine theta all squared over the cos of theta. Oops, not correct. Sorry about that. It's incorrectly written. The whole thing is in the bracket. Let me just write it correctly. All squared. Plus I got exactly the same thing, but with a minus, I think, on the top. All squared, and this ought to give us 2 plus 4 tan squared theta. Okay, is that an elegant identity to prove? Probably not. It looks another one like loads of algebra, like the previous one. I don't remember where this question is coming from. I had these questions for a very long time. Some of them might be from the 90s even. Okay, so what is the best, well, definitely we're going to be a left-hand side, but what is the best approach for something which looks like this? Okay, me, you know, I've done a mistake in the beginning and I wrote this in a bracket all squared. It's probably better to actually do that on the next line, is to actually rewrite it. That's definitely correct. To say, you know what, that is that squared over cos squared. And the reason for that is quite clear. It's because we're going to get a common denominator. And then, of course, I'm gonna save a line this time because I'm getting a bit tired of writing too much stuff. I want to put them together and put the cos squared at the bottom. What follows after that is quite clear. I just need to tidy up this numerator. If I square the first bracket, it's going to be 1 plus 2 sine theta plus sine squared of theta. The bracket has a plus at the front, so it's quite safe to expand it. 1 minus 2 sine theta plus sine squared theta, the whole thing over a cos squared of theta. At least something cancels. These have gone, and I've got 1 plus 1 plus 2 sine squared theta over cos squared theta. I'm nearly done. I just need to see what is the best way now to proceed from there. I don't want to factorize the 2 because if I factorize it, it's going to produce a 1 plus sine squared. I don't think that is an identity or useful even. What is the best approach from there is to actually split the fraction for 2 reasons. Purely because 2 over cos squared was going to give me sec squared, and a sec squared is related to a tan squared by identities, and also the other split, which is sine squared over cos squared, produces a tan squared, which I'm seeing in there. So splitting the fraction is going to give me 2 over cos squared theta plus sine squared over cos squared is of course 2 tan squared of theta. I don't have the right amounts of tan squared. I have 2 and there's 4 in there, but I have this extra term in there, and I'm going to write it as 2 sec squared of theta plus 2 tan squared of theta. And then there's of course the Pythagorean identity that says 1 plus tan squared theta is equal to sec squared theta. So the sec squared is 1 plus tan squared, so I'm going to write this as 1 plus tan squared theta plus 2 tan squared theta. And of course after that 2 multiplied out, 2 tan squared plus 2 tan squared is 4 tan squared of theta, which of course is my right hand side, and the identity is proven. When I didn't mention for this particular question, there is another approach which is a little bit sensible. It's not that bad. I don't know if you can see, if you split the fractions within the brackets, you're going to get a sec of theta, that's the 1 over cos, plus the tan of theta all squared. And you're going to get a similar expression, 1 over cos, again a sec, but this time minus a tan of theta, all squared. When you simplify this, you're going to get a sec squared of theta from both brackets. I'm not showing workings here, by the way. I'm just going to you can try that in your own time and just check it for yourself to see what happens. You're going to get a 2 sec theta tan theta, but you're going to get exactly the same term from this, so that will cancel, but with a negative. And you're going to get also a plus 2 tan squared of theta after you expand and simplify that. And if you look at this line, you're going to get, of course, to this line here. And probably, in retrospect now, thinking about it, this is probably a slightly better approach. It kills a lot quicker and far more efficiently than what we've done. But it's okay. I mean, on a Monday, Tuesday, Wednesday, I'll do it like this. Thursday, Friday, Saturday, I'll do it like this. And on Sundays, I'll rest or something. So don't worry too much about it. Okay, that's enough for today. Up to 21, I will continue with 22 to as many as I can again to just give you more practice. And for the time being, who's laughing now?